from the University of Graz in Austria, who is presenting us the talk entitled Large Deviation Principles for Lacunary Sums. So thank you very much again, Joscha. Whenever you're ready, it's your turn.
Thank you. Yes, thanks for asking me to give a talk in your seminar. So I'll present a recent work which is not completely finished yet. And this is joint work with Christoph Aistleitner, also from Graz, and Nina Gantert in Munich, Zakhar Kabluchko in Münster, and Kavita Ramanan at Brown University. And essentially it all, let me say a little bit how this all started. So I think it was last year when I was reading the autobiography by Mark Katz, and he somehow explained the beginnings of probabilistic number theory and all the nice results, his central limit theorem with Erdös and so on. So and since David and I think it was about 4 years ago that we started looking into large deviations, or the study of large deviation principles. So the probabilities of rare events. Then I somehow asked myself, so Katz explained all these nice results of Erdös and him and Salem and Zygmund, but there seemed to be nothing about large deviations. And then we started looking into this question when we met in Oberwolfach this year. So this was it was the last meeting before the lockdown, essentially. Yeah. And today what I'll present to you are the findings that we got during the last 6 months or so. Okay, so let me start. 1 second. So let me start essentially at the very beginning. Okay, so I'll take you on a short journey to motivate the question that we were looking at. And it goes back to the golden 20s, essentially, when Rademacher in 1922 studied the convergence of what we now call Rademacher series. So you have a weighted series here of bk are just real numbers, and rk are the Rademacher functions, or the Rademacher random variables. And the question was about the convergence of these random series. Yeah. And what Rademacher found out was that such a series converges for almost all omega in the interval 0, 1 if this weight sequence is in L2. So this was in 1922, and just a few years later, Khinchin and Kolmogorov continued this line of research. They said, okay, so we know now if B is in L2, then we have convergence almost surely. And what they found out is that the condition that B is in L2 is also necessary. So it's if and only if. So this was in the 20s, and it concerned the study of Rademacher series. And if you look at at the structure of a Rademacher function, then you see that, okay, instead of looking at such a series here, I can look at this series where I replace just the RK. I can rewrite it, just as a series of dilates of a fixed function. So I have my dilates here, 2 to the k minus 1, and I look at a fixed function. And somehow this, and also this, so the Rademacher random variables are +1, -1. So they're periodic, and this somehow triggered the study of the so-called Lacunary trigonometric system, or Lacunary trigonometric series, which are a series of this form. So you just replace this R1 of 2 to the k minus 1 by something more general, in a sense. Yeah. So you look at what I call a Lacunary trigonometric series with weights bk, and you look at the cosine of 2 pi ak omega, and your sequence ak that appears here. So this replaces this 2 to the k minus 1. This is a Lacunary sequence, which means it's increasing sequence of positive integers, and it satisfies a certain gap condition, the so-called Adamar gap condition. So it's increasing, and ak plus 1 divided by ak should not be too small. It should be above some q, which is larger than 1. So this is somehow somehow natural generalization of this Rademacher series. And what Kolmogorov found out in 1924 when he studied this Lacunary trigonometric series is that also those series converge almost surely if B is in L2. So we remember we had this for the Rademacher series. This was Rademacher's result from 1922. And this is the equivalent in the Lacunary case. And it was quite a few years later that Zygmund again continued this line of research and found out that also in this case, the condition that the sequence B is in L2, so it's square summable, is a necessary condition. So these Rademacher series on the one side and the Lacunary trigonometric series on the other, they satisfy the same L2 dichotomy. So this was a connection that was observed, and then one was naturally led to the study of the Lacunary series. But there was one thing that remained unobserved for quite a long time, and this is a kind of innocent observation I start with now, which is somehow trivial, and we all know it. So if we look at the Rademacher system or the weighted Rademacher system, then this is a sequence of independent and centered random variables with a certain variance and so on. So, and then we go back and think, okay, so there's Lindeberg's central limit theorem. And then I can check that this Lindeberg condition, I'm not going into details, but this is satisfied if B, our weight sequence, is not in L2, and the maximum of the B case for k between 1 and n is little o of the L2 norm. Okay, so whenever your weight sequence satisfies this, then Lindeberg's condition is satisfied and you have a CLT. In particular, this holds if bk are equal to 1. So just think of Rk now. So you have the Rademacher random variables, they satisfy the CLT. So we have such a central limit theorem. And Lindeberg proved his CLT essentially, when was it, in 1921 or so. So this is an old result. And while we had this dichotomy and we understood that, okay, the Rademacher series behave in a sense like the Lacunary trigonometric series, this probabilistic aspect here that I'm mentioning, this innocent observation, this was not transferred for a long time to these Lacunary systems, to this Lacunary trigonometric series. But it is a natural question. So we have this central limit theorem in this Rademacher setting. So what about Lacunary trigonometric sums? Do they satisfy the central limit theorem? And just to make sure that there are some obstacles here, right? Those random variable xk here, they're identically distributed and uncorrelated, at least if all the ak are distinct. But they're not independent, okay? So it's not so trivial here. It's not so simple. They're not independent. So and Katz, Mark Katz was the first one to prove such a probabilistic result for the Lacunary trigonometric series, and he proved that an analog CLT to this Rademacher setting holds if our Lacunary sequence, these are AKs, are far apart, super exponentially far. So AK plus 1 divided by AK tends to infinity. Okay, so I have really large gaps in my defining sequence. So in that case, if you have large gaps somehow, we see that essentially those Lacunary sums are like independent random variables. But this was just a special case of large gaps. And then quite a few years later, it took some time to establish the central limit theorem in the general case. So under this Adamar gap condition. So I not only just have a CLT if I have these huge gaps between this defining sequence, this Lacunary sequence, but also if it just satisfies this Adamar gap condition. So AK plus 1 divided by AK is larger than some Q, which is larger than 1. Okay, so if I have some gap which is large enough, then I have a central limit theorem. And the result of Katz somehow was during the time when probabilistic number theory was born. This was about the same time when he proved his central limit theorem for with Erdös and so on. So that a number of results appeared. So this is the one by Salem and Zygmund, and then people started looking into other questions. So Salem and Zygmund and Erdös and Gall in 1955, they showed that, okay, it's not only a CLT that can be proved for Lacunary trigonometric sums under a Adamar gap condition, but we can also establish a law of the iterated logarithm for these trigonometric sums, Lacunary trigonometric sums. So they showed that almost surely we have that this Lacunary trigonometric sum here divided by root n log n, so just a little bit beyond the normal fluctuations, the lim sup is equal to 1. So those are all classical results, as I said, and they're described nicely in Katz's autobiography. And the philosophy behind those results, there are more results, it's just I picked some of them. The philosophy behind all those results is essentially that Lacunary trigonometric sums behave somehow like sums of independent random variables. But of course, I have no independence, because I can write this here. This is essentially cosine 2 pi ak and u is uniformly on 0, 1. So I have the same random variable there, and it's all essentially deterministic. So what makes this this independence come in somehow is this gap condition. But as long as I have this Adamar gap condition, I can prove CLT, I can prove a law of the iterated logarithm, I have a law of large numbers, which goes back to Hermann Weyl, which follows from the ergodic theorem. So everything we know somehow, the classical results, law of large numbers, law of the iterated logarithm, CLT, they hold. But then, as I explained at the very beginning, so what about large deviation principles? What about large deviation principles? And let me recall, because I think David already gave a talk about large deviation results, and he explained to you what it is. So roughly speaking, it's the study of rare events. So the strong law, or the law of large numbers, tells us something about the typical behavior. So if I have centered random variables, then partial sums normalized by n, they tend to the expectation. So this is typical behavior. So if you say you take a value that is beyond that typical value, the expectation, then this probability goes to 0. The probability that Sn divided by n is larger than some number a, if we're in the centered case, then of course this goes to 0. And large deviations tell you how fast, essentially. They tell you that it's an exponential decay, because just the quantitative bound that you would get from Chebyshev would tell you something, it goes like 1 over n, but actually what the Chernoff bound tells you, it goes exponentially fast to 0. These rare events, the untypical behavior is exponentially small. So roughly speaking, if you have a sequence of random variables, then we say that it satisfies an LDP, or a large deviation principle, with a speed Sn. Later, this will always be n. N will be the speed. And a rate function I, which is typically lower semi-continuous. If for sufficiently large n and sufficiently regular sets, so essentially Borel sets, then the probability that psi n is in A is more or less e to the minus Sn. So the speed, in our case, it will be n, times the infimum over x and a, I of x. So I somehow determines the rate, and this Sn determines our speed. So these probabilities of the rare events depend on the speed and on the rate function. And in many cases, this can be computed. So the question is now, David, how much did you say about large deviations? Did you define what a large deviation principle is?
I defined it long ago, so if you recall everything, that's better.
Okay, so then let me try to. Okay, 1 second. Can you now see my iPad? David?
No.
No. Let me check. So now I should share my screen again. So can you now see it?
Now we
Okay,
can.
perfect. So yes, so this is the rough idea. Let me just write the definition again, and then I continue. So if we have a sequence xn and an n of random variables, say just real, okay, just real valued random variables, then we say that they satisfy an LDP, a large deviation principle, with speed Sn and lower semi-continuous rate function. Okay, rate function by definition is always lower semi-continuous, so we have compact level sets. Yeah? So, and lower semi-continuous rate function, which I call I, from R to 0 plus infinity, and it may take the value infinity. So this satisfies an LDP. Yeah, satisfies an LDP. By definition, if and only if the following holds. So for all, say, A in R Borel, we have that minus the infimum over all x in the interior of the set A, I of x is less than or equal the limit inferior, n tends to infinity, of 1 over Sn, this is my speed, logarithm of the probability that xn is in the set A. This is of course always less than the lim sup. N tends to infinity, 1 over Sn log probability xn in A. And this should be bounded above by minus the infimum over all x in now the closure of A, I of x. Okay, so you see, so this is the definition of a large deviation principle. So maybe it's easier if I tell you what a classical result is, namely Chromier's theorem, which looks a bit simpler than this at first weird looking limiting condition. Yeah? So a classical result goes back to Chromier, and I think it was 1933. Yeah, and he showed the following. He showed that if you have x1, x2, and so on, they're IID random variables, and they have all finite exponential moments. Yeah, so for simplicity, let's say they have finite exponential moments everywhere. Yeah, so random variables such that lambda of t, which is the log moment generating function, this should be finite everywhere. Yeah, it's enough if it's finite in the neighborhood of 0, but let's say we ask for it to hold for all t. And if we have those random variables and we control all the exponential moments, then Chromier tells us that then for all t larger than the expectation, yeah, so it's a non-typical behavior, yeah, this is what I explained before, then the limit as n tends to infinity of 1 over n, this is my speed, this was my Sn before essentially, log of the probability that x1 plus xn, so the partial sum, is bounded below by n times t. This is minus lambda star at t, and this is the Legendre transform. Legendre transform of lambda. Okay, so this classical result tells you that these partial sums here, yeah, normalized by n, decay exponentially. Yeah, so this says the probability that Sn divided by n is larger than t behaves more or less like e to the minus n, and then I have my lambda star of t. Okay, very roughly speaking. Yeah, and this is the idea behind large deviations. They just generalize this concept. Yeah, this is because asking for a definition like this somehow, that you have that the limit is equal to something, turns out to be too restrictive to allow you to produce a nice and rich theory. Okay, so this is just transformed into this a little bit weird looking condition. Yeah, but essentially what you study is rare events, and this is what you can think of. Yeah, so a large deviation principle tells you something like that we have an exponential decay here. Yeah, and Chromier is just a special case of the partial sums, yeah, normalized by n. Yeah. Okay, so I hope now everyone has at least a rough idea what a large deviation principle is, and then let me try to go back to my slides. So, can you now see my slides again?
No, we still see you, right? But now we can.
Very good. Okay, so this is a large deviation principle. Yeah? It generalizes the idea behind Chromier's theorem that you want to study the probabilities or the asymptotic probabilities of rare events. Yeah? Okay, so, and we have seen that under this Adamar gap condition, we have a CLT, we have a law of the iterated logarithm, we have Hermann-Weyl's law of large numbers, and it all seems to be that, or what we see there for these Lacunary trigonometric sums, is that as long as we have this Adamar gap condition, as long as we have this, we have these probabilistic results. And what we found out when we studied large deviations, the rare events, then we found out that unlike in the CLT or the law of the iterated logarithms, on a large deviation scale, so beyond this root n or root of n log n, so if we're on a scale of a law of large numbers where we normalize by n, so the large deviations, then these principles somehow are sensitive to the arithmetic properties of this sequence. Yeah, it's not just this Adamar gap condition, which is enough somehow to get something like to get these large deviation principles, but somehow they're very sensitive. Yeah, depending on how this Lacunary sequence behaves. And this is related, I'll not go into details today because this would go too far, to certain Diophantine equations, yeah, to the numbers of solutions in certain Diophantine equations. Yeah, but let's just say those results we found out are sensitive to the arithmetic properties of these sequences. So let me start with the first result that we could prove. And this is, of course, where did we start? We started where Katz started like 80 years ago. So he looked at this large gap condition. This was the first thing he proved. Yeah, under not just the Adamar gap condition, but if we have super exponential growth, if we have really large gaps in the sequence AK, then he proved the CLT. And this was also our starting point of investigations. Yeah, so we said, okay, so what happens if we have this large gap condition? Yeah, and what we found out is that, okay, the normalized partial sum, so Sn divided by n, yeah, if we have a large gap condition, then they satisfy a large deviation principle with speed n. Yeah, so I have an exponential decay in n, yeah, and a rate function I twiddle. So now what is I twiddle? So if I go, so look up here. So my Sn, so my xk, my random variables that I study are these cosines of 2 pi aku and use uniformly in 0, 1. So they're all, it's not independent. That's what I said at the very beginning. Yeah? So I do not have, I have identical distribution, but I do not have independence. Yeah? So what do we get if we look at a similar sequence, but with independent random variables? So we take u1, u2, and so on, uniformly distributed on 0, 1, independent, and I define xk twiddle to be the cosine of 2 pi ak uk. So now I have a sequence of independent random variables, and their distribution, you can check, is the arc sine law on -1, 1. Yeah, but this doesn't matter now. Yeah, so they have a nice distribution, they're independent. And then you can show that they also satisfy a large deviation principle. So Sn twiddle divided by n with a convex rate function, I twiddle. This is finite on -1, 1 because this is where the arc sine law is supported here, and outside it's plus infinity. Yeah. So what we found out is that under the large gap condition here, if your sequence grows fast enough, then you get an LDP as for independent random variables. Yeah, so we found out, okay, if we have large gaps, then they behave in the philosophy that I mentioned before, like independent random variables. Okay, this is maybe not really unexpected in a sense. Yeah? This is somehow what we expected. Yeah? And one can prove it. And I want to explain to you how this is done in a special case, yeah? Because then it's quite instructive. Yeah? So yeah, here again, you see that this is, of course, the difference. While here we have dependent random variables, here we had independence, but since the gaps are large enough, the rate function is the same in the end. Yeah? So the idea behind the proof of this result is the so-called Gertner-Ellis theorem. I'm not going to state it. Let me just say that to show that our random variables, or that our Lacunary trigonometric sum, you know, satisfies a large deviation principle, it is enough to show that such a limit here exists. Yeah? This is just the log moment generating function. You divide by n, take n to infinity. If this limit exists, yeah, and is equal to this here, which you get for the independent. Remember, Sn twiddle are always the independent random variables. So if this limit exists and is equal to the independent thing, and this function is differentiable everywhere, then you get the LDP. This is what the result tells you. Okay. So how does the proof work? So I restrict myself to a simpler case because otherwise it's way too long. So we take now ak plus 1 divided by ak to infinity. Yeah, this is our large gap condition. And let's assume for simplicity now, for this proof I present, that ak plus 1 divided by ak is a positive integer. Okay, this makes the proof easier. Yeah? So xk is now this random variable here. And by definition, this is 1 over ak periodic. Yeah? And xk plus 1 makes exactly mk, so ak plus 1 divided by ak, full oscillations on each of these intervals. Yeah? So maybe before I continue in the proof, I'll draw a picture. So let me go back to my iPad. So 1 second. Can you now see my iPad again?
Yes.
Okay, very good. So it's just a very rough picture to give you the idea now. So we have these random variables xk, and somehow we want to make things easier. So we use an approximation. Yeah. So I draw it like this. Okay. So let me draw it above this. So let's say we have our function here. I have my 1 over ak 2 over AK, and so on. Yeah? And then I have it like this. Yeah. So I draw it above. Yeah. So I don't mingle here with my line down here. Okay. So this is my XK, let's say. Yeah. This is my XK. Yeah. So this continues here in this manner. So XK is cosine 2 pi AK. Yeah. And this is 1 over AK periodic. Yeah. So, and in the next step, okay, I go down, I say, well, I have here my 1 over AK plus 1. Yeah, this is, let's say, imagine this is much bigger. Yeah. So I have here 1 over AK plus 1, 2 over AK plus 1, and so on and so on. Yeah. And then I have here my oscillations. Yeah. So I have this here and here. Yeah, and so on. Yeah. So this is my XK plus 1, cosine 2 pi AK plus 1, and this is 1 over AK plus 1 periodic. And I make MK, which is AK plus 1 divided by AK, full oscillations. Yeah. Here, yeah, in each of these intervals, here and there and there and so on. Yeah. So this is what I'm dealing with essentially, and what we're going to do now is, well, we approximate our random variables by something easier in a twofold way. Once we choose it constant on these subintervals, yeah, and second, we do it in a way that we get independent random variables. Yeah, and then all we have to make sure later is that these approximations are good enough. Yeah, but essentially somehow that I get something independent. Yeah, so, and I will do this in the following way. I choose random variables yk to be certain conditional expectations. Yeah, and these are then constant if I choose the right filtration. Yeah, so I choose random variables yk, and fk plus 1 is the following filtration that you get from looking at the intervals I ak plus 1, I plus 1 over ak plus 1, and I between ak plus 1, between 0 and ak plus 1 minus 1. Yeah? So look at these filtrations, and then those conditional expectations are somehow constant, yeah, on these intervals, so simply by construction. Yeah, so I approximate here by my conditional expectations. Yeah, so this is the idea, and then hopefully, or the proof shows us that this is good enough. Yeah, but by construction somehow I get something independent. Yeah, and the approximation that I have here, somehow this is good enough. Yeah. So this is the picture you should have in mind now. You have this oscillating things. You have full oscillations. This is why this works nicely. And then you approximate by your conditional expectations, which are constants on these blocks. This is the one advantage. The second is they're also independent. No? Okay, so let me go back. Let me go back to my slides now. So can you see my slides now again?
Yeah.
Yes.
Very good. Okay. So you all have the picture in mind now. Okay. We have our oscillating beast there, and then we approximate. We'll make it easy. Yeah. So as I wrote down on my iPad here, so you take this, now just formalizing the picture somehow, what I'm doing, not more. Okay. So I take my filtrations here, F1, F2, and so on, and Fk plus 1 is just the filtration that you get by generating the sigma algebra from all these intervals here. I divided by ak plus 1 up to I plus 1. Yeah, so you get all these little blocks. Yeah. There, the conditional expectation is by definition constant. It's written here. It's your yk. It's the conditional expectation of xk given fk plus 1. And this is just the sum here. And then on jk plus 1 comma I. Yeah, this is just one such interval. Yeah, so we have this all split into parts. Yeah, so this is our conditional expectation of xk. Yeah, so from these dependent random variables xk, I go to the y case. Yeah. And again, what is the benefit of this trick? Well, the yk are independent. They are constant. Okay, they're constant on these blocks. This is I didn't write here. And they are good approximations of my original random variables. Because somehow I need a good approximation. Otherwise, I cannot make this transition from dependent to independent. So what does it mean, good approximations? In the following sense, that the L infinity norm of xk and yk is bounded above by 2 pi ak over ak plus 1. Yeah? So I tell you right now that the proof I present here does not only work for cosine, but you can use more general periodic functions in this case, as long as you have Lipschitz continuity. Yeah? So you see here the Lipschitz constant of our cosine, right? So why does this condition hold? Well, you just go down to one of these intervals. Yeah? I divided by ak plus 1 up to I plus 1 divided by ak plus 1. You look at the max overall omega here. Yeah? And then you compare xk of omega with our conditional expectation. This is just written here. So you get this is equal to the maximum of xk of omega minus, this is the conditional expectation on this interval. This is what I wrote on the slide before. Yeah? Now you use the mean value theorem. So you find some y naught in this interval somewhere, yeah? Such that this here is equal to the maximum of xk of omega minus xk at this point y naught, or omega naught, I should have written. Yeah. And this I can bound above simply by the maximum of 2 pi ak omega minus y naught. Yeah? And this is bounded above because I have my gaps there by 2 pi ak over ak plus 1. Yeah? This cannot go beyond that. Yeah? This is because this is exactly my interval. Yeah? It's I divided by ak plus 1 up to I plus 1 over ak plus 1. Yeah? So I have good control about on the L infinity norm of my original random variables and the conditional expectations. And by now maximizing overall I see that also the partial sums here, I mean, I get it then on everywhere. Okay, if I maximize over I get this up here. Yeah? And this transports to the partial sums. Yeah? So if we now look at Sn, which is our original partial sum that we're studying, the x case, and I look at this independent counterpart, which is constructed by these conditional expectations, then I see that this bound above gives me also good control about Sn and Sn twiddle, this independent thing. Yeah? And the control is little o of n. And if you now think back again about what I said, what a large deviation principle is, or about Chromier's theorem, then you had this 1 over n times log. Yeah? And this 1 over n, this can kill my little o of n, of course. Yeah? That's why this is good. I call it good control, yeah? Because this vanishes in the end, yeah? This error that I get, yeah? On the logarithmic scale or on the scale of a large deviation. Yeah? So I also have this control. And then I just split my expectation of my log moment generating function here in the following way, that I write it as the expectation of e to the theta, the independent part. This I can treat by Chromier, right? And this error part, this can be bounded above and below by just saying, okay, it's e to the minus theta times this error is of course less than this, is less than e to the theta, again my error, and again this independent part. This is nice. So I have that the thing that I'm studying can be compared with the independent one up to an error that I control. So, and since this error is little o of n, as I said before, I get this result here, that the expectation of e to the theta Sn compares with e to the expectation of e to the theta independent thing up to something of order e to the little o of n. And on the large deviation scale, where I look at 1 over n logarithm of this vanishes somehow. Yeah? So I get essentially what I want. So I get this limit here. And because the function here, the limiting function I get, this is somehow a modified Bessel function. This is differentiable. I can compute it explicitly. It's a modified Bessel function. It's differentiable, so I can apply Gertner Ellis. Recall Gertner Ellis said you need to prove this limiting condition. And if the limiting function is differentiable, then you get the LDP. Yeah? So the limiting function is a modified, or the logarithm of a modified Bessel function. And then I can apply this theorem and I get theorem A. Okay.
Excuse me, Joscha.
Yeah.
Yeah, just one question to the previous slide.
Yeah.
So the little n, the little n that bounds the error between the Sn and the independent.
Yeah.
It very much depends on the choice of AK plus 1 divided by AK on the behavior of the Lacunary thing. So
yes,
because of your hypothesis on the Lacunary, then you obtain the little n.
Exactly. Yes.
Okay.
So this is what I used there. So to bound this, I mean, I went over it pretty quickly, but yeah, I really used that this tends to infinity, right? So I get this little o of n because I have the sum up to n and this Lacunary part there, this ratio, and since this is small enough, I get this little o of n.
So okay.
So again, so in the case that we have large gaps, we see that I have behavior of my Lacunary sums as in the case of independent or sums of independent random variables. So next step, okay, let's look at geometric progression. So I don't have these large gaps, but I have AK is equal to some q to the k, and q is some integer, 2, 3, 4, and so on. Yeah, one of these integers. And now I look at these. So I don't have that this gap tends to infinity anymore. Yeah? I just have this geometric progression. And then we can prove that the random variables again satisfy a large deviation principle. Again with speed n. I should write it here. I didn't write it. Again with speed n and a rate function iq, which is different from the independent one. So now you do not have these large gaps. And then you get an LDP, but not as in the independent case. But as is to be expected, as when you make this gap larger and larger and larger by increasing q, by sending q to infinity, yeah, you make the gap larger, again, you end up somehow in the independent case. Yeah? But remember, in the CLT or so, as long as you had a gap condition, which we have here, we have behavior as it is for independent random variables. This is not the case here somehow. You get a different rate function. So what you can, so the proof, I will not present the proof. So this is pretty tricky. It uses some general results on thermodynamic formalism and expanding maps of 0, 1. So this is quite delicate, but you can prove it. And you can also show that this function iq is at least on 0, 1, always strictly less than than the I twiddle, which you get in the independent case. Which means that a probability of a large deviation of a Lacunary sum occurring is asymptotically larger than in the independent case, right? Because you have the e to the minus n and then the rate function. Yeah. So in the independent case, this rate function is bigger, so your probabilities are smaller. Right? So probability of a large deviation of a Lacunary sum, here in the geometric progression case, is asymptotically larger than in the independent case. Okay, so you see that you do not get the behavior. So this is really sensitive somehow to the arithmetic structure here, in the sense that this is not the independent rate function you get. So going again back to Salem and Zygmund's result, so they showed that Sn divided by root n satisfies the CLT under the Adamar gap condition. So this is really sufficient. This is not the case on the large deviation scale, because you can show the following. you can construct a sequence. This is by mixing up some of the sequence that you construct is mixing up some powers of 2 and 3, 2 to the k, 3 to the k. You mix these up, and since you can construct a sequence ak of positive integers that satisfies the Hadamard gap condition. But Sn divided by n does not satisfy large deviation principle. So don't read, I mean, this is just more detail, but it does not. So an Hadamard gap condition is not enough. So in CLT and LIL, in the law of the iterated, it is enough, but not on a large deviation scale somehow. This is kind of maybe surprising. This is unexpected. So what do the previous results somehow seem to tell us, or what do they tell us? Well, it seems like the limit of this Lacunary sequence, ak plus 1 divided by ak, determines my rate function. Because you had seen in theorem A, if we have huge gaps, then it's the rate function as for independent random variables. And also for the LDP rate function to be this, one could think, because of the other theorem I presented, that you somehow need this to get to infinity. So we had an LDP for the geometric progression, which was not the one we got. It was not itwiddle. For the geometric progressions, we had an LDP with a different rate function, and for these huge gaps, we had the independent one. So this is, so you could guess now, this is really needed. You need huge gaps, and then you get independence. Because also in the other result, you had that if Q is large, then again you go to the independent case. So it really suggests that you need huge gaps. But this is again not the case. It's again not the case, and again surprising. So the large deviations are really sensitive to the arithmetic properties, because you can show the following. So there is a sequence AK such that AK plus 1 divided by AK tends to 2. So it's not large gaps. It's more like in the geometric progression when Q is equal to 2. So you can construct a sequence AK, so it's somehow a random perturbation, such that AK plus 1 divided by AK tends to 2, but the random variables satisfy an LDP with the independent rate function. You could think that somehow, okay, if AK plus 1 divided by AK tends to 2, you're in this geometric progression case, and there you got the random, the rate function I2. But this is not the case. So it's really, so these large deviations are really sensitive to your sequence. It's just you have this sequence which tends to 2, which is essentially the sequence 2 to the k that you take and put on it an additive random perturbation of smaller order. So you take your 2 to the k, this geometric progression thing, which gives you a rate function which is not the independent one, and then you take a lower order random perturbation on it, and then suddenly you get the LDP with the independent case. So you see somehow, so this is what I said right now, so you see that these random perturbations completely or can completely destroy this underlying dependence. And this is also unexpected and we find quite fascinating. This is all behavior that you do not see in the CLT and in the law of the iterated logarithm. So one last thing. So the natural question is, so what happens on the sublacunary in the sublacunary case? So this means that not AK, so AK is comparably small. So log AK divided by K tends to 0. So the AKs do not increase too fast. So it's sublacunary. So you do not have an Hadamard gap condition. And then you could still think, okay, so before we had mixed results, but we had with a certain speed n, we had these large deviation principles. Under the Hadamard gap condition, somehow but now you do not have this Hadamard gap condition. And then you also do not have an LDP, or at least not a non-trivial LDP where the rate function is constant 0. Because you can show that if you have a sublacunary sequence, you do not have an LDP with speed n. So maybe at a different speed, I don't know, but not at speed n. And the proof goes as follows. So there really we have the rare events decay slower than exponential, yeah, in n. And the proof is very simple. So if you have this sublacunary case, so pick some z in 0, 1. Then, of course, so you think of your cosine. Then you can choose a small neighborhood around 0, such that cosine of 2 pi omega is still larger than your z, as long as your neighborhood is small enough. Yeah. So for all omega in a small neighborhood, you're still up there, above that. Yeah. So this means in particular that your random variables here, or cosines, are also still larger than z. If I put in the ak here, as long as omega is now less than or equal delta divided by an. Yeah. Okay, so I have to make it, as long as I make it small enough still, my neighborhood, also my random variables are above that. Yeah. And how does this help? Well, look at the lim_inf of this logarithm of the partial sums to be larger than z divided by n. This is the object that we're looking at. This is what you have to look at in a large deviation principle somehow. So this is bounded below by the lim_inf over the logarithm of the probability that each xk is larger than z. Of course, if each zk is larger than z, then also the average is larger than zk. So this is of course a lower bound. Yeah? And then this is bounded below. Here we use this. Yeah? As long as omega is less than delta over an, we have this condition here. So if I apply this here, I get a lower bound of the form limit n to infinity log the probability that omega is less than delta over an. This is just using this here. So, but now this is, my omega is uniformly distributed over 0, 1. So the probability is here just delta over an. So I have this log delta over an divided by n, but here I have the sublacunary condition. So log ak divided by k tends to 0. So the whole thing here is 0. So you see that on a sublacunary scale, if you leave this Adamari gap condition, then either, well, then you do not have exponential decay in n. At least not without a non-trivial rate function, which is 0 everywhere, which is a bit boring. Okay, so to sum up again, so while all the classical probabilistic results like CLT, LIL, the law of large numbers hold for Lacunary trigonometric sums, in the sense that they hold like that you have the behavior like independent random variables, everything changes on a large deviation scale. Yeah, and there interesting things happen as you saw, right? Large gaps, you get independent behavior, geometric progressions, it's different behavior, and so on. Yeah, so it's really interesting to study these Lacunary trigonometric sums on a scale of large deviations, because they're sensitive to the arithmetic structure of this Lacunary sequence, contrary to the scale of the CLT and the LIL and so on. Okay, so thank you for your attention. That's everything.
Okay, thank you very much, Joscha. So if anybody has any question, you can unmute you, I think, and ask Joscha.
Yeah, I think in what you call randomized perturbation, it was 2 slides before, in the 16, I think.
Yeah.
Yeah, just to make sure, just for my own understanding.
Yeah.
So when AK is exactly 2 to the k, we are in the
geometric progression case.
In the Rademacher, in the original case, which in this, so of course this would not be a counterexample, but to anything. But in the case AK is exactly 2 to the k, so the theorem is just a refresher. So the theorem would say, you understand my question?
Yes.
Just to compare with what it means related to the theorem. Just
if you have AK is 2 to the k.
Exactly 2 to the k, yes.
Yes, then it's the case as in the geometric progression somehow.
Yeah. Yes.
2 to the k, just q equal to 2. Then you have a large deviation principle with speed n,
Okay.
the rate function, which is really different from the rate function you get in the independent case.
Okay.
It's really different. It's strictly less than this. Yeah.
Okay.
So, and now you take your sequence 2 to the k, where you know if you just choose this, you get an LDP with a rate function I2, and then you perturb it a little bit, lower order perturbation. Yeah.
Okay.
And then you also get an LDP with speed n, but now the rate function is the one from the independent random variables.
Okay, I see.
And you might could expect somehow, okay, if I just wiggle around a little bit, perturb of a lower order, this should have no effect, and I get my rate function I2 again. But this is not the case. So it's really sensitive regarding the arithmetic structure. You have your AKs 2 to the k, and you change it a little bit. Yeah, and you think you do not change too much, but somehow, with respect to the rate function, you change it a lot. Yeah?
Okay.
Yeah.
Yeah.
This
Yeah.
Unexpected.
Yeah. Okay, I have another question. Have you also looked at moderate deviation principles? If you normalize the sum by something between square root of n or between n or n?
Yes, so this is the project that we have. So this paper will be finished, I hope, next week. And then we start looking into moderate deviations, because because on the CAT scale, root n, Adamar gap condition is enough. Then even if you go somehow a bit further, because if you look at the law of the iterated logarithm, you still have this root n, log n, you're still in the behavior of independent random variables. And then suddenly on this large deviation scale, this is very sensitive. And now we want to look at the moderate deviations. So between this CAT and the LDP, and see if we can find a point where this breaks somehow, where at some point maybe the arithmetic structure of the AK kicks in and starts to change things. Yeah, so it makes it sensitive. And before that, maybe it is not. You're more on the CAT scale, and at some point it's sensitive to the arithmetic structure. But yes,
maybe
this is
different ranges where different situations happen.
Yes, yes. But this is this is the follow-up project that we're looking at. Yes. But we have no results yet.
Okay.
Yeah.
So anybody else has any question?
Okay.
No. So then we thank you again. We cannot.
Yes.
You cannot hear clapping, but we are.
Yeah, my pleasure. No, thank you again.
Thank you for your talk.
Thank you very much, Joscha.
Okay, then please stay well, everyone.
Yes.
And I hope to see you in person soon after lockdown.
Yeah.
Let's hope.
Yes, let's hope. Okay.
Okay.
Perfect. Take care, everyone.
Take care. Thank you. Bye.
Bye. Bye.
Bye.